Welcome to the demo of virtual prototype quick start package from Circuit Sutra. In this demo we will demonstrate the package for UART, MMC and SSP. Before we start the demo, let's have a quick look at the contents of these packages. VPQSP UART. It has the TLM UART protocol which defines the transaction level interface for the communication between two UART modules. It has the convenience socket, TLM UART socket, that implements the complex serial protocol inside it. So anyone who want to develop the model of a UART controller need not worry about implementing the complex UART protocol. They can simply instantiate the sockets and use the APIs. It has the model of the CST terminal that encapsulates the terminal window on the host computer. It has a TLM UART socket through which it can connect with the UART controller. The package also has a sample model PL011 UART. On similar lines, we have the VPQSP MMC. It defines the transaction level protocol for MMC. It has the convenience sockets for the controller side and for the card side, which implements the complex MMC communication. So anyone who want to develop the model of a MMC controller or the MMC card need not worry about implementing the complex MMC communication. They can simply model their registers and call the APIs of these sockets. The package comes with the sample models PL180, the model of the MMC card and model of the SD card. And similarly we have this VPQSP SSP which defines the TLM SSP protocol. It also has the convenience sockets for the SSP master and SSP slave, and the socket implements the complex SSP protocol inside it. So anyone who want to develop the model of a SSP master or a SSP slave need not worry about implementing the complex SSP communication. They can simply model their registers and call the APIs of these sockets. The package comes with the sample models PL022 SSP and SPI flash M25P80. To demonstrate these, we will use the CST board, which is the virtual prototype of a sample SoC based on ARM Cortex A15. It is capable to boot Linux and can be used for embedded software development. The models used in the board are developed using Circuit Sutra modeling library and VPQSP. So this is a high level block diagram of this board. It has the model of a ARM CPU Cortex A15 which is based on KMU. So we have extracted the CPU core part from KMU and developed a systemc TLM 2.0 wrapper on top of that so that it can be used in systemc based virtual platforms. It has a TLM 2.0 bus and the models of several peripherals. CST board has the models of minimal peripherals required to boot the Linux, like timer, interrupt controller, memory. Apart from that, it has the models from various quick start packages. So in today's demo, we will focus on PL011 UART, PL180 MMC and PL022 SSP. So let's see the demo. So we can first have a look at the source code. So this is the source code of CST board, CST board.h. Here we have a model CST board which has instances of all the peripherals, plus it has the interfaces for connecting with the CPU model. This is the CPP file. So in this, this is the instance of PL011 UART which is registered on the TLM bus at a particular address space. So whatever TLM transaction comes for this address space will be handled by PL011 UART. The UART socket of PL011 is connected with the UART socket of CST terminal. So whatever data communication happens through the UART controller will be displayed on the terminal window. Similarly, we have instance of PL180 MMC. It is connected with the MMC card. We have instance of PL180 MMC, another instance. It is connected with the SD card. We have instance of PL022 SPI controller. It is connected with the SPI memory. So let us see the demo. So in the CST release folder we have the demo setup. Here in the docs there is a file quickdemo.txt which lists the steps for the demo. The first step is to set the environment variables. For that we have provided a script. For Windows it is cst setup.bat. Okay, so let's have a look at this file cst setup.bat. So to run the CST board, primarily we have to set two variables, CST rel, which is path of the CST release folder, so that CST board can pick up the DLLs from the right location. It has the environment variable for CST config file. So config file actually specifies the configuration parameters for various models. So let's have a look at this file. So like we have defined the configuration parameters for SD card, MMC card here. The next step is to start the virtual platform. So for this we have to run this executable CST board, and we have to specify the path to ZImage and bootloader. So in CST release RVP CST board, in the utils folder we have this ZImage and bootloader. We will specify these. In the bin folder we have the executable. So I am going to run this executable now. So here I am running this executable CST board a15.exe. I have specified the path of ZImage. I have specified the path of bootloader. I am running it now. So it has opened a terminal window. This terminal is the model of CST terminal, which has the UART socket attached to it, and through the UART socket it is connected to the PL011 UART controller. So all the Linux boot messages are coming on this terminal. From the boot message we can see that Linux had identified all the peripherals that were connected on CST board, like MMC card, SD card, other devices, SPI memory, etc. So let's start with the demo. So UART package is already demonstrated through this CST terminal. So when Linux is booting, all the messages are being directed to the UART controller, and through that it's coming to this terminal window. These are getting displayed, and whatever command we run on this terminal, this will go through the UART controller to the Linux running on CST board. Linux will process it, and whatever output comes, that will again be directed through UART controller to this terminal. So that demonstrates the UART. Now let us see the demo of the SPI memory. So SPI memory is actually defined as a MTD memory in Linux. So when the Linux boots, it should be able to identify that. And if we see the content of this file proc/mtd, we should be able to see the configuration of that memory. So I am going to see this cat proc/mtd. So here we see the details of this SPI memory, which is recognized in Linux. The name is mtd0, size is 8 MB, the name is SPI mem. Okay, so we can write some application which actually use this SPI memory using the mtd commands or the APIs, and we will be able to access that. Now let's see the demo of the MMC card and SD card. So for MMC card and SD card, it must have created the device files MMC BLK0 and MMC BLK1. So let us see this. /dev/mmc star. So we see these files MMC BLK0 for MMC card, MMC BLK1 for SD card. So these are raw card right now. So before using these, we will have to format this. So I am going to format it now. mkfs.bfat/dev/mmc BLK0. So it formats the MMC card. Now I will format the SD card /dev/mmc BLK1. So it is formatting the SD card now. So now we will have to mount it on some temporary directories. So I am creating two directories, mkdir mmc, mkdir sd. I will mount this /dev/mmc BLK0 on this MMC, and I will mount this /dev/mmc BLK1 on this SD. Okay, so the cards are mounted on this directory. So now we can actually transfer some files on this. So I will try to create some file. Let us say echo. So I am creating this file in the MMC folder. So it will be automatically created on the MMC card. Similarly, let me create a file on the SD card. I am creating this file in the SD folder, hence it will be automatically created on the SD card. So the files are created. So let us see whether these files are there. ls mmc, I see this file mmc.txt. I can see the content as well. The contents are there. Similarly, let me see the SD card. The file is there. The contents are there. Okay, so these files are created on this card now. So that means if we see the host computer, here they have created the two temporary files are created, MMC memory and SD memory. So whatever file system we have created from the virtual prototype and whatever data we have transferred to it should have been stored in these files. So if I close the virtual platform now and start it again without deleting these files, then we should be able to see the same data again. So we will try that. So before closing, I will unmount this first. I am unmounting, unmount /dev /mmc blk0. Oh, the command should be umount /dev /mmc blk0. So it's unmounted. I will unmount the SD card now, /dev /mmc blk1. So both these cards are unmounted. Now if I see the contents of this folder MMC, so I will not see anything. Similarly, if I see the contents of SD, I don't see any data here. So I am closing the virtual prototype now. And I am starting the virtual platform again. So if I do ls, so I don't see the directories here MMC and SD because these were created on the Linux image. So these have been lost. So I will have to create those again. So to use the SD card and MMC card, I will not have to format this now because these were already formatted and we have not deleted those files. So we will just have to mount these. So I am creating the temporary directories MMC, SD, and let me now mount /dev /mmc blk0 on the MMC. It's mounted. I am now mounting /dev /mmc blk1 on the SD. It is mounted. So let me see whether we have the data now. ls/mmc. Yes, we see the file is there. Let me try to see the contents. mmc/mmc.txt. Yes, the contents are there. Similarly, we can see the SD card. So we are able to see the contents. So the model of the card actually stores the data on the host computer. So that's why this storage is persistent. So that completes the demo of this virtual prototypes, quick start packages. So all the models in this CST board, they were actually developed using Circuit Sutra modeling library, which is a collection of convenience classes and utilities, which is the model development activity. It also has a model generator utility. So you can define your interfaces in some Excel files and it will automatically generate the model and the test bench, etc. The primary benefit of CSTML is whatever models you developed using CSTML, they automatically becomes tool independent and can be integrated with any virtual platform tool. Another benefit is, the models automatically becomes the platform independent. So the models will be automatically supported on Linux 32, Linux 64, Windows 32 and Windows 64. And the models were using the virtual prototype quick start packages. The VPQSP is a library of basic models and modeling infrastructure. It contains the TLM protocols and the convenient sockets for the popular chip interfaces and the backend modeling infrastructure to access the host computer interfaces. Like for the SD card and MMC card, we use the file system of the host computer. Similarly, for other interfaces like USB, we can use the USB interface of the host computer. For Ethernet, we can use the network interface of the host computer. So when a virtual prototype is developed using CSTML and VPQSP, it can result in the reduction of the development efforts up to 80% for the complete SoC or the complete electronic systems. So that completes today's demo. Thanks.